Now, ironically, guys, would you call number 12's graph a parent or a kid if you're thinking in context of children, of functions?
It's a kid.
It's a kid. Why is it a kid? I totally agree.
It's scooted that way.
It's scooted. Scooted and it's stretched. How do we know that it's scooted and it's stretched?
Because it's scooted.
Oh dear. What's the parent?
Stop.
Y equals x is the parent, right? 0, 0, 1, 1, 2, 2, 3, 3. What changed in this one? Didn't the slope change?
Yes,
because the slope is no longer 1, so that changed from the parent function. And the intercept is no longer at 0, 0. So, Alec, we were trying to get a feel for the parent functions on Friday in class so that we would recognize a kid when they came, right? And anybody in psychology, without going too out there, if someone is having issues, they go into a psychologist. At one point, what's going to come up in that conversation?
Their health.
Maybe
Their
how are you?
mental stability.
Their mental stability, they're going to go looking at their history. Right? Like, when did this start? Where did this come from? How did these behaviors, even in the Bible, they talk about parents' sin being passed on from generation to generation. Or you guys can even do, or look into studies of like alcoholism and different things like that, as far as some things are seemingly tendencies toward genetically passed down. But partially also we're all depraved and broken and crave things other than God for satisfaction. But coming back. Sure. No, literally, food's a thing, right? Some people crave food, some people crave things that are much more detrimental to their health than others' health. Number 22, another kid. But who's the parent?
X.
Square root of x, which means, well, square root of x should be down here, so he's been shifted up and over, true?
Yes.
Wait,
left 2.
how is he shifted? It's
Up
plus
3,
and plus.
left
Why
2.
is he going negative?
Negative minus 2
Backwards what
opposite.
you think. Now, this is where it got interesting. Isabella was that kid. Oh, it was the other
the
one?
ones that it like says to grab, like on your calculator. How do we do that? Because you can't really show what.
Oh, just okay. But make sure in showing directions and problems that you give me the function then the sketch.
On calculator.
Oh, man.
Okay, number 28. Who got something wrong? Come on, someone did this one?
I
Who
got
got
all
this
of
one
them.
wrong?
I got that one wrong. I put negative 18.
I got B, C, and D wrong.
Okay, pause. Let's go back and look at that Steffi function. He was the one that I explained with parking garage, right? Parking garages charge by the hour, not the minute. Usually, unless they're the really cheap kind. Cheap kind, expensive kind, whatever. We'll say parking garages charge by the hour, not the minute. What do I mean? If you've been there 1.5 minutes, well, technically, parking garages would be like shifted up and over one, probably. But either way, the first hour free. Yay! Now, technically, for a parking garage, that would probably be filled in. But once it goes a second past 1, now it's charging up here, then it's charging up there, then it's charging up there. But parking garages, the decimals don't matter. Now, if I were to give you like a little shortcut for how to do step functions, I would say round down. Now, why is that weird? If I say round, isn't it sometimes up and sometimes down? What's the cutoff between rounding a number?
0.5.
Yeah, if it's the previous digit, whatever that previous digit is it above 5 or below 5? Is it below 5 or greater than or equal to 5, right? Whether to round up or to round down. But I don't say round up ever. I say round down. Because do you guys see that point 9 is at what height? 0. You see it? 0.1, 0.7, 0.9, all of them are 0. 1.1, 1.9, 1.5, 1 are all 1. 2.1, 2.3, 2.72, all 2. Round down, which would help you with all of these except letter D, depending on how your brain works. Round 1 down, well, it's still 1. Round 3.5 down is 3. Round 7.2 down is 7. This is easy. Round negative 18.6 down, negative 18.
I didn't round it down.
You guys had to plug in and then simplify. So maybe if you didn't get here, you didn't plug in. You got negative 18.6?
No, I just like I
I got
And I
11.6.
just
Big bro.
I just got rid of the decimal, so I did -21.
You have to do PEMDAS. You have to do the grouping symbols first and then do the operation. So kind of like if you were to do something like f of x equals x plus 2 squared, and you were plugging in something like f of 3, you have to do the 5 before you square it, not the 3 squared, 2 squared.
But it's only -21.6.
Well, you can't round him until you've done the inner operation. Now, on this one, sorry, I know it wasn't this function. I was trying to relate it to something else. Can you guys tell me what the original function was? Oh, it's this guy, right? Plus 3? Okay. So if I go to plug in for -21.6, let's pull it up here. I would get you probably still made the same mistake, to be totally honest. But technically, according to PEMDAS, you have to do what's inside the operation or the grouping symbols first. So you would need to add, which would be. But mostly, what your question is why is it -19 and not -18? You guys saw the stair step going down, right? Okay. So, where were the stairs here? Can we check out the graph? Where would -0.5 be? Why was -0.5 -1? Or why is -1.9 -2? And -1.1 is -2? And -1.0001 is -2? Is it working differently? No. See, it continues the pattern. It's stair step down. But guys, what's below, what's lower than, what's down from a decimal? -1/2. If I round down, it is -1. -1.1. If I round down, it is -2 because -2 is lower on the number line. So if we come back here, -18.6, the graph might be a little confusing. It'd be way over there somewhere, which is kind of awkward too. But basically, you would be down here. Oh, solid. There we go. Is that right? Oh, that's solid and that's empty. Yeah, I had it backwards. Way easier when you do the whole thing to see what's going on. So it's way easier when you have the whole thing to see what's going on. Can I actually get out of this graph altogether and just go to good old-fashioned number line? Didn't I say round down? So if I was to say round down, let's just pop up one real quick. Here's my 7, here's my 8, here's my -18, my -19. Just for examples, right? 7.2 would be here-ish, right guys? Rounding down, it would be 7. That's easy, right? Where's -18.6? Here-ish. Round down. It's the same thing. I'm rounding down. It's just weird because the magnitude of my number gets bigger. If it was a positive, I would round to 18 because 18.6 would be farther away from the 0. I'd be going down. So the positive ones make hopefully really clear sense because we're used to rounding with positive numbers. Negative numbers just get weird because technically rounding down puts me at the next lower negative number. Jaden.
Should we have done this without our calculator? Oh, I did it with my calculator.
There's a great integer function in your calculator.
There's a what?
There's a step function in your calculator.
I put absolute, like the absolute value signs, and then I did that. I don't know if that would work.
The absolute value would have made it a positive 18.
Yeah, everything was positive that I got. I don't know.
But you wouldn't have gotten to whole numbers, would you? How'd you get
No,
to
everything was. Okay.
Don't do absolute.
No, thank you.
But in your notes, remember there were two different categories. So step function is one special type of piecewise, and absolute value is another
I wasn't here for that. And I didn't watch the video. Sorry.
It's okay. It's like question time. Number 40. You guys are supposed to graph, right? He's a funny double check your holes in your filled in because that's really important as far as the or equal to's or not or equal to's. And then number 48, you were talking about domains and ranges for some of the different given information. I could scroll down a little bit. There we go. The nice thing is, I think we went over most of that in class. I guess we didn't specifically write down the increasing, decreasing, or the intercepts. But in the sketches, you guys should have been able to pull out the domains, range, intercepts, and then increasing, decreasing. And the parent function, the non-transformed function, the parent function has a nice even and odd symmetry, but as soon as you go shifting up, it's away from the x-axis, it's away from the y-axis and the origin. It won't be even or odd. It'll have some symmetry that mimics the parent, but it won't be around the y-axis or the origin as soon as you shift away. Oh, one more. False. False. But it would have seemed totally true unless you thought of horizontal and vertical lines. Vertical lines only have one x. Horizontal lines only have one y. Any basic line's going to have domain and range of all real numbers, but the horizontal vertical ones, they kind of are counterexamples to that always being true. With that, cool kids, I think we're done with grading. What questions do we have? Anything you want us to go over? Yeah, Sophia. Yeah. Oops, I was trying to get over there. For the letter C, right?
Yeah.
Oh, it's because the book has a different agenda than I do. So, oh wait, no, they did do the exact same way. When we were talking about increasing and decreasing in class, I told you guys to always keep the intervals open, and here's why. At 0, isn't there a change from decreasing to increasing? So even though the graph includes 0, I'm not going to include 0 with the decreasing side or the increasing side. That's not my call to make. Does that make sense? It's the in-between. So if I group him with decreasing, well, why wasn't he increasing? If I group him with increasing, well, why wasn't he decreasing? If I group him with both, so wait, both are happening? He's more of an in-between than he is a value that should be included in one category. Does that make sense? Think of him as Switzerland. No side.
You go over 40.
40? 40?
40.
I need a hand. Okay. Oh, come on, Mr. Hand. There we go. 40 was the piecewise function. You guys are trying to sketch the graph. Okay, this one, my advice for a piecewise function is get your particular x values. Those are my little separators. So -1's an important one and 1's an important one. And to be honest, I cheat. Because normally when you graph a line, don't you go to the y-intercept like 0, 1, and then go up 2, over 1, up 2, over 1, right? But I'm not allowed to use 0. So actually, I'm just going to use -1 and plug it in. Okay, oh, -2 plus 1 is -1. Sweet, well, I know you're there. And then I could go, if I wanted to be really snazzy because I know slope, I could go down to back 1, and I'm like, okay, cool.
So you just pick something that would work within that, and then that would get your y, and then your x.
And remember, whether or not this is or equal to, I still need the placement. I still need where it would be. So if it was not or equal to, I still would have plugged in -1 because I need to put a hole there.
Right.
Does that make sense? And then as soon as I get to this guy, okay, it's not or equal to, but I still need to plug in -1 and say, well, where are you? Well, that'd be 2 minus 1, which would be a positive 1. If I'm putting a hole there, because he's not or equal to. Does that make sense?
Yeah.
And then I could plug in 0, -1. I could plug in 1. I just plug in some in between because I know that he's a swoop, or he's a parabola, which would be also back here. Right? And then plugging in 1, once again, I know it's not or equal to, there's going to be a hole there.
2.2.
1 would be 0, right?
So it's greater than 1.
Yeah, but I'm going to plug in 1 because I want to know where would he have been so I can build off of that.
Okay.
Because remember, I need 1.1, 1.2.
And what has to do with the open circle and the closed circle?
Remember, closed circle is when I have an or equal to, it says include, which is y include, which is why I included all the way up to x equals -1. But if it's not or equal to, it says bounded by, but not including. That's when I say, okay, it's bounded by, but I have to show it's not allowed to be there. That makes sense. I would have to keep going. Sorry, I don't know. 2, that's 4, -3.
Okay.
Any other questions? Anything else you guys want to see? Is it time to go get to the kids?
No. Let's just leave them both.
Those kids. All right, section 1.7. Those kids. I think I put that homework online already. But you guys are amazing. You haven't checked your phones, right? Just kidding. You had your tuition. Yes, homework number 7 is due tomorrow. So we need to get going with the kids. Now, you've talked about transform functions last year, right? Did you get them okay? Okay. That's a no?
What?
That's a no? That's a no? Oh my goodness, everything's trying to say. Okay, let's get to section 1.7. Oh, that's not very exciting. Let me have you guys write down mirroring or reflecting. Can we make sure I didn't skip dilation though? Where's dilation?
Small for A.
You guys already wrote that down though, right?
I did not.
Wait, what?
What? It was up there like all at the beginning of class.
I was talking to you about it.
Alright, there we go.
Wait.
This table of contents is obviously super high IQ.
There we go. Okay, so for those of you guys that did already take page 1, go ahead and take page 2. Because translations and reflections are the easiest transformations. Translations and reflections are the easiest transformations. Dilations, where it gets a little bit tricky.
Wait, so we have to write the little box?
Translations and reflections are the most basic ones as far as the easiest to see and to do. Dilations are where it gets a little bit iffy. So translations, let's start there. Transformations is the big category, is the general category of, okay, it's time for the kids, aka the parents have changed. We have the behavior of the parents in the back of our minds. So if we see a square root, like, okay, it's kind of like this, but maybe it's been reflected or stretched or shifted. So how do we see what's going on? Well, with translations, there can be 2 different ones. Now, in general, for all the transformations, here are a couple things that I try to keep in mind. If we're talking about inside transformations, they're going to be horizontal changes. If you have inside transformations, don't worry, you'll see what I mean in a second. Inside transformations, they're going to be horizontal, and they're going to be weird, and I'll talk about it in a second. And then outside are going to be vertical, and not as weird. Now, I would love to say horizontal or backwards, but technically isn't always true. Opposite, that's not technically always true either. But both of those words sometimes are appropriate. Inside, horizontal, basically what I mean by weird is it's acting differently than what you expect. Isn't that normally what the word weird means anyway? They're weird. That just means they're acting differently than you would either like or you would expect. Right? So, okay. Inside horizontal, outside vertical. Why am I saying that? What's going on as far as these transformations down here, the translations, which of them are occurring inside the parent function? Both 3 and 4. And what kind of shifts are those? Horizontal. But what's weird about them? There's a minus. Which way am I going? The positive way. And there's a plus. Which way am I going? The negative way. So when are they weird? They're operating or they're moving, changing backwards than I would think in this case. But then what changes are happening outside the function? Vertical shifts, which is normal. Plus means go up and minus means go down. Okay, cool. We can call them shifts or we can call them translations. This is called a rigid transformation because the graph itself, like if I had absolute value of x minus 2, I'd be shifting the graph 2 to the right, but my shape didn't change or stretch. It stayed the same. Mirroring or reflections. Once again, the shape doesn't change. The snazzy term for that is rigid transformations. Maybe you'll see that in your vocab. But reflections. Guys, what do you notice about, well, this one's weird. I don't see the word vertical or horizontal, so I guess my clue just kind of broke down, right?
Negative on the outside.
Although there is an outside and an inside.
That's good.
So wouldn't the outside one, according to my trick, wouldn't that go with vertical? Outside is happening to the function, to the f of x, to the y's. The vertical's changing. This one's inside, horizontal. Well, how does this make sense? Because this one says x-axis. That doesn't go with vertical, and y-axis. That doesn't go with horizontal. But wait. Reflection. Doesn't that kind of mean flip?
Yes.
If I flip across the x-axis, what kind of flip is that? It's the vertical one, isn't it? What's up is down and down is up. So it technically is a vertical flip is what we could call it. The snazzy way is though saying, oh, it reflects over. So this one is describing the over. It's reflecting over the x-axis, but to go over, what's up is down and down is up. That's a vertical flip. So a couple different ways of describing it. So technically my trick does work. It's just a little weird. But the changes are occurring to the y's, to the vertical units. And this one is going to be a horizontal flip because if you flip across the y-axis, isn't what is right becomes what's left and what's left becomes what's right? So that'd be a horizontal flip. Yes, we would call it a reflection in the y-axis because that's what it's going over, but technically the flip itself is still along with my clue, outside vertical, inside horizontal. So what are we missing? Translations, reflections, stretches. But guys, I skipped the example page because we're going to have more examples. So let's just not stress, because those were the easy ones, not stress. Let's just get all the transformations in. What are all the things that can happen?
Distortion.
What are all the types of kids that can become? We have the inside ones, the outside ones, the weird ones, the normal ones. Now we have the non-rigid ones. Non-rigid means the shape does change. It could be a stretch or it could be a shrink. But I like using the word dilation because then I can name it before I figure out whether it's getting bigger or smaller. Or being stretched apart or shrunk in. If I say dilation, I'm like, it's either one. So I'm right both ways. But the shape does change, that's why it's called non-rigid. You guys see how, once again, it can happen outside to the whole function or inside to the x values? Outside vertical, inside horizontal. I'm going to write a couple words to see if this helps, though. Which one's the weird one? The one that says, hey, if I multiply by a big number, it gets bigger, and small number, it gets smaller? Or the one that says, when I multiply by a big number, it gets smaller, and small number, it gets bigger?
I'm lost.
Yeah. This one's the backwards one, this one's the weird one, but that's okay. The horizontal one's all the time. We didn't really talk about how the reflections are weird. They're not as weird. But this horizontal one is the weird one, so can I just quickly give you a hint about the weirdness? Let's just actually call it that. The horizontal weirdness. There you go. Remember, weird, it's nothing derogatory, it's just different than what we expect. Sure. Just careful. Depending on how you use the word special, it might be derogatory. Don't do that. Same thing with weird, depends on how you use it. But in my case, I'm just saying different other than what we expected. The horizontal weirdness for dilations. So there's going to be a dilation and a horizontal dilation at that, by a factor of 1 over c. That's the weird thing. If it gives me a 2, it's shrinking because it's dilated by 1/2. If it gives me a dilation or a c of 1/3, it's growing by a dilation of 3. It's the reciprocal of what I expect. For translations, some of you already know if there's a minus, I'm going right. If there's a plus, I'm going left. Like that's one that you've seen multiple times. What's a little bit weirder is the dilation one, because with horizontal, if you see a 2x, that basically means it's happening twice as fast, which means what was happening at 2 is now happening at 1. What was happening at 1 is now at 1/2. What's happening at 1/2? What's happening at 1/4? In essence, your graph gets shrunk in because it's happening twice as fast. But that's confusing, and so it's a little bit easier just to say, okay, whatever value you see being multiplied, dilations, there's a multiplication going on, it's going to be 1 over what you see. The actual overall effect horizontally is 1 over what you see. So 2 twice as fast, sweet. Everything happens in half as much time. Which in the real world kind of makes sense, but in math it just looks confusing. Looks confusing. Let me see what I have on the next page. Oh, no. Really? Haha, you guys ready? Example. What's on the next page that I'm hiding right now is usually what I save for the next day, for the opener. But the dilemma is, when I show you number 9, most of you have gotten very frustrated in homework with number 10. So you come in being like, ugh, there was one of those in homework and it was so hard and it was so confusing. This example that I'm about to show you is actually not with a parent function at all. Well, it is, but not with one that you're familiar with. It's really just kind of like a weird piecewise function. You guys have number 10 in your homework that looks an awful lot like number 9. And if you look at number 9, they're like, we don't even want you to be thinking of y equals x squared or y equals x cubed or y equals the absolute value of x. We don't even want you thinking of that. We just want to call this dude f, give you his 4 points or his 4 representative or his 4 main points. We can call them his parent points. For a parabola, one of the parent points would be the vertex. He's one that we have to go to and look at. Maybe the behavior of both of the branches going the same direction. For a cubic function, one of his parent or his main points is the point of inflection, and then kind of like his direction. There are some key characteristics from parents that help me out when I'm doing transformations, but this one says, I don't even want you thinking about those parents. Besides the fact that you just have this weird graph with 4 points, do you know what to change? Now here's the struggle, guys. How many different changes do we have to do?
4.
I see 7. Do you see 7? 7 changes to 4 points, right? 7 changes to 4 points. Now, could that get messy? So what's one way to try to not have to reinvent the wheel and do the same thing over and over and over again, but still make it actually make sense? Could you use 7 different colors? Could you make this 7 times? Could you maybe do like 3 different colors on 2 or 3 different graphs? I mean, strategize, but it's going to be a mess if you try to do all 7, although that's exactly what I'm going to try to do because of 10. 7 of these colors. Ready? Here we go. Before I ever, this is important, before I ever go to the actual points, we're going to think about what changes. So in letter A, guys, what changes?
Y.
Is it a shift, flip, or dilation?
Flip.
What kind of flip? It's on the inside. If it's on the inside, it is horizontal, the same thing as y-axis flip. Yeah, good, over the y. Okay, how about letter B?
Up.
Shift, and then specifically you could say up 4. How about letter C?
Vertical stretch.
Vertical, stretch. Can I just do, that way I'm not wrong. But yeah, 2 is going to make it grow. How about letter D?
Reflection x-axis. And
It's going to be a vertical flip because it's on the outside. And it's going to be
right 4. Or shift. Up.
right 4, right? How about letter E?
down 3 or shift.
Shift down 3. How about letter F? I wonder what the order should be. I wonder if the order is important. How about letter G?
Horizontal
Shrink. Is it a shrink or is it a stretch? What's the factor?
shrink because it's small or because it's bigger.
See it? Twice as much time is going to happen in half the distance. So you can always take whatever is in here for horizontal and take the reciprocal, and then it's going to tell you, oh, half? Okay, cool. That's going to be a shrink. 2, oh, that's going to be a stretch. Now, how do we do all of those when we come over here? Wait, if it's a horizontal flip, for this one, if it's a horizontal flip, doesn't that mean whatever was at a positive 6 is now going to be over here at negative 6? Does that make sense? So instead of positive 6, 2, isn't it going to be negative 6, 2? And instead of negative 4, 2, isn't it going to be positive 4, 2? I'm going to take each of my x's and flip the signs. Only the x's. And flipping 0 is still just 0. And then once I get my 4 representative points, couldn't I, very carefully, sketch it? So horizontal flip is going to flip the x's. What's, for instance, the vertical flip going to change? The y. So instead of going negative 4, positive 2, it's going to be negative 4, negative 2. But wait, aren't you going to then have to take that and go over 4 also? My advice is step-by-step color code. There's only one really nasty one like this. It's number 10. Let's see how you do. But the rest are a little bit more straightforward. Come with homework questions tomorrow. There might be a few. You guys will get time in the morning before class starts, though, to talk about corrections if you need any help from your group. But I'm also here after school.